Okay, we've talked about delta H or enthalpy, which shows us a heat of reaction. We've also talked about delta S or entropy, which shows us a measure of disorder. So now we're going to talk about a measure of spontaneity, and that's known as delta G or Gibbs free energy. And as far as the values go, if delta G is a negative value, then it's going to be a spontaneous reaction. Whereas if it's a positive value, it's going to be non-spontaneous. This should kind of be ringing some bells because we've talked about spontaneity when we talked about electrochemistry. And when we talk about it being spontaneous, we're saying it's spontaneous in the forward direction or it's not spontaneous in the forward direction, but we're always talking about it in terms of the forward direction. And if we happen to know the temperature is at 25 degrees Celsius. If you look at your reference sheet that you were given that has all the values for these things, your H, S, and G on there, you'll notice in the heading it talks about 298 Kelvin. Well, that's 25 degrees Celsius. So if it's at 25 degrees Celsius, you get to use Big Mama. So it's going to be the same reaction except we use the column for our delta G instead of S or H. So if it's not at 25 degrees Celsius, then we need to use a different equation, and it's going to be delta G equals delta H minus T times delta S. So essentially what this does is it tells us that this Gibbs free energy is, the change of that is equal to our total energy change, and we subtract the energy that's lost in the process of getting it disordered. So that's how that equation works. A couple important things to remember. Our temperature has to be in Kelvin. If you're ever in question about that, just look at the headings on your reference sheet and you'll see that your temperatures are in Kelvin. And then also, my other caution about the units is that if you look under your S values, your entropy, you're going to notice that it's not kilojoules, but it is joules. So what you're going to end up seeing is that you're going to want your delta G values in kilojoules. Your delta H values are given to you in your data table as kilojoules. You're going to subtract T times delta S. Well, T is going to be in Kelvin. And then your delta S, the way it's given to you on your data table is as joules per Kelvin. So you must convert that right up front before you can ever plug it into this equation, and you must convert it to kilojoules per Kelvin. And then that way everything will work out nicely. So that's the big thing to think about is your delta S value. Oops. I don't know where it just went. Hold on. There we go. Okay, so here we're just reiterating what we just said. There's the equation, and then as far as our delta G being less than 0, that's if it's going to be a negative value, then it's spontaneous. If it's positive, it's non-spontaneous. Here's our first example. We are reading through this and we want to calculate delta G, but we're told it's at 25 degrees Celsius. So we know this is going to be pretty easy. All we have to do is use Big Mama. And in this one, we're just going to say our delta G value is equal to, and we look over at our products, we've got our carbon dioxide, 1 mole of that, times, and I look in my delta G column, and this is the value I find, plus, and we've got 2 moles of water, and we look that up, and we see it's negative 237.129. We're going to take that and subtract the delta G values for our reactants, which is going to be 1 times our methane, which is negative 50.72, plus 2 times our oxygen, which again is going to be 0. And when we go through this math, we end up getting our delta G value equal to negative 817.897, and that's going to be in kilojoules. And the question was to calculate the delta G, but if you were asked, is this spontaneous or not, the answer would be, yes, this is spontaneous. Now in this next one, we notice that it's not at 25 degrees Celsius anymore. Instead, it's at 100 degrees Celsius. So we know that we have to use our reaction that we were given earlier. Meaning we have to find delta H values, delta S values, and delta G. Let me just go through our delta H real quickly with you, and then maybe I'll pause it. And let's see here. I've lost my place. There we go. 295.830, and then we subtract our reactants, which is 174. Okay, so hopefully you're following along and you know what to do there. You're just doing Big Mama where you've got products minus your reactants, and in this one we would get a negative 890.359. That's going to be in kilojoules right there. I'm going to go ahead and do delta S, and let's see, we're calculating delta G. I'm going to go ahead and do delta S for this next one, but I'm going to pause it and just let you see it when I've written it down. All right, I went through the same process with my delta S, but now is what we need to really make note of. Notice that our delta H value is in kilojoules, our delta S is in joules per Kelvin. So in this case, we've got to make sure that we do some conversions before we can plug it in. And let's just make ourselves a note that this is going to equal negative 243.0 joules per Kelvin. What we end up having to do, we have to say that there's 1,000 joules in 1 kilojoule, and we end up getting a negative 0.243 kilojoules per Kelvin. So that's what we're going to end up throwing into our equation, and our equation, remember, is going to be delta G equals delta H minus T delta S. So when we throw this in, we get negative 890.359, and that's in kilojoules. Maybe you still want to write that down just to safeguard yourself. Make sure that you made that conversion. And then we're going to subtract our temperature, and it has to be in Kelvin, so we need to add 273 to our 1,000, so it's 1273 Kelvin. And then we multiply that times our delta S, which is negative 0.243 kilojoules per Kelvin. So now we see that Kelvin cancel, and we're left with our kilojoules. We're just subtracting that, and when you go through that math, you end up getting negative 581 kilojoules. So there is your answer. Again, that is going to be spontaneous.